now we start the final talk of the SGU lecture given by Professor Fedor Malikov. Title is Introduction to Algebras of Chiral Differential Operators.
So, quick reminder. So if you look at this simple so you take this one-dimensional this one-dimensional manifold and that cotangent bundle. It's two-dimensional. What is it? Two-dimensional supermanifold. Of course, obvious checks. And obvious transformation functions. The most important one was that d equals this. On the intersection. Then properly understood. Properly means very little. That's not even trying to understand them. It's even more helpful. Properly understood gives an isomorphism of the corresponding. Yes, this is the fancy notation. That's just the restrictions of the putative so far Chiral Durham complexes to each of the charts. And so define the desired example, the Chiral Durham complex on the projective line. So defined previously was this thing without any out coordinates. On hindsight, the existence of this sheaf is just a coincidence of the low dimension. It's just one-dimensional thing. It's easy to prove that. You'll see later that any one-dimensional manifold variety carries a sheaf like that. So one could think that such a naive approach is not going to work usually, but it does. So let me quickly formulate the main result about the Durham complex, and then we will move on. So the existence of the Durham complex owes the fact of existence, owes its existence to, the following coincidence, following miracle. So it's a universal fact. So consider formal disk. That's the ring of functions on it. Once we have functions, we can play the game I explained and obtain the Chiral Durham complex of this type. So just the Chiral Durham complex on very, very small. Remember, I explained how localization is defined, and for that we need any convergence. The only thing we needed from a function that would be differentiable arbitrarily many times. So there you are. Then this naive formula has the following even more naive suggestion. So you take the group of automorphisms of this ring, let me call it A, and you equally naively cook up a map that gives you linear transformation of that shape. Permit me to save time by not writing the corresponding formula. The explicit formula is an exercise. A very simple one. It's an exercise not in vertex algebras, but in elementary differential geometry. You just, what's an automorphism? It's a coordinate change. Xi goes to the phi. Now there are several variables, but chain rule will give you similar classic formulas for the transformation of functions and vector fields. And just insert these and interpret this as a map on the fields. Suppose you are a C student in vertex algebra, so you don't realize that not all fields can be multiplied, not all associativity fails, and blah, blah, blah. You just lift it to a map of vertex algebras. The probability of it being an automorphism of vertex algebras is 0, but it is. That's the content of this lemma. So you have this huge set of linear maps, linear transformation on the set. And inside there is a subset of automorphisms. So lemma says that the naive map defines a group homomorph. In fact, obviously an injection from automorphisms of the formal disk. That's right. To the group of automorphisms of that vertex algebra. So this computation amounts to what I did for you in the case of P1. The general case is harder only computationally, but not conceptually. So either try doing it on your own. If not, look up the paper of 98 where this was done. So the immediate corollary of this is there is a natural rule that to each smooth variety X, smooth algebraic variety, but in fact it's smooth in any sensible meaning of this word. C infinity analytic doesn't matter. It's not a map, of course, it's a rule that attaches to it a shape of vertex algebra. Yes.
So just to clarify, so formal disk means formal disk, not polydisk.
Formal, just formal series.
So the X's are the same as, so there's infinitely many X's?
Finitely many. It's a non-dimensional formal disk.
Individual formal disk.
Mm-hmm. It's just dream. That's what I wrote. I actually wrote what I thought. I sometimes write not exactly what I think, but in this case I was honest. Arbitrary, everything is arbitrary. Another corollary. That's a very tiny part of this discussion. If a Lie group acts on X, then there immediately arises the action not only of I don't want to do the loop groups. Let's not worry too much about it. Let's do the infinitesimal version. I think loop groups will work just as well, but so in particular, of course, G maps to vector fields. If so, then there immediately arises the map of the action of the loop group on the sections of, gives the LG equivariant structural LG's action of the action of LG on the corresponding the RAM complex. Even more is true. It's not just the action of the loop group, it's the morphism of corresponding vortex algebras. I'm not making any assumptions on G. So what I mean is the most, well, you know what I mean. It's, I don't know anything about central extension or anything. Any group will do. But if you once you have a loop group, you can define the a vacuum of L module and define the corresponding vortex algebra. But if it's you know, a simple group, then there are extensions, things like that. But so the level is 0. So V acts on the current device. And in particular, to return to that example, we get a map of SL2 to the RAM complex on P1. And these formulas easily allow you to write down this equation explicitly. So E of Z will go very similar to what we did in the case of, in the purely even case. I'm just using coordinates on one of the charts. Can you guess what f of z, where f of z will go? It's on the board, like it was in the case of CDO on P1. This formula, of course, that the change of variables is, what's the name of this automorphism that swaps C and F? Chevalier or something? This is famous automorphism of a Lie algebra that sends positive roots to negative ones. So that's exactly what happens. F will go to this thing. Does this, well, but except that, of course, now the tildes are to be removed. And of course, I mean fields and the normal ordering and stuff. This had better be contrasted with the situation of with a purely even situation when we had a similar map. This is the critical level. So that's the hallmark of the Chiral Differential complex. While in general things may or may not exist, and if exist may develop quantum corrections like the shift of the level, here we have this stable, you know, nothing really happens. These formulas are just as suggestive as the corresponding formulas in the even case were. Of course, this is the Wakimoto, the famous Wakimoto realization, except that now the level is 0. Observe that there is a fundamental difference. At the critical level, there is center which can be killed, and we've obtained the smallest possible such module. And here we have a blown up, the full-fledged Wakimoto module. So for people who only start getting acquainted with this area, it's the point where the boson fermion correspondence is to be recollected. So this product of two fermions gives you a boson, and that's, of course, Wakimoto didn't have any fermions; he didn't have to. So what we have has, you know, fermionic grading. So the actual meaning of these formulas is on one of the charts. The space of sections is like this. So we have the grading by fermions. So the with respect to the corresponding Clifford algebra, so rather for the corresponding boson, the highest weight vectors are 1, psi minus 1, psi minus 1, psi minus 2, etc. Phi naught, phi minus 1, phi naught, etc. And so growing under the action of this whole thing, well, no, not the whole thing, but the beta gamma system encoded in X and L, and the boson. You get a highest weight vector growing from each of such vertex. And the point is that each of those restricted to the SL2, these are all locomotive. That, of course, contains the global sections. And that's given by the simple lemma. Think about it. Prove it if you like. So the way global sections are, of course, the embedding of global sections agrees with fermionic charge. What you have to do is to take, I will put SL2 on top. I don't mean the SL2 invariant part, I mean the SL2 integral part. Meaning the maximal SL2 integrable submodule. Like that's the space of global sections. Such things have a filtration by Weil modules. So each such thing is filtered by, so each such thing is filtered by Weil modules. Exactly how this filtration is arranged is precisely known. It's not obvious. There is a technology for that. So I think I'll stop here, not to get bogged down in too many details. Are there any questions? Yeah, just to finish with this. So I think I mentioned it already, and now I will reiterate, because that was one of the sources of early interest in this construction. So we now have this thing for an arbitrary x, and the graded object is this famous vector bundle that I discussed. So there will be symmetric powers of tangent and cotangent, and reflecting the odd variables, exterior powers of tangent and cotangent. And so the Euler character of this thing, for me by definition, but there is a topological definition of this object, and then Riemann-Roch says that the Euler character is exactly or rather one of the elliptic genera attached to X. I've had a discussion over these days with colleagues about algebraic geometers who were interested in this subject. And I'm ashamed to realize that I forgot to mention one who really made an outstanding contribution to this whole subject, including this simple but very important remark. Baristov, of course. He actually used, in a rather non-trivial way, the Chiral-Durand complex to discussion of mirror symmetry. So I'll probably say a few words and leave it there. So if X is toric,
You really need Borisov.
Borisov.
But you can write down the
Ah,
originals.
sorry. So if X is storic, you know, it is defined via all kinds of combinatorial data. Most importantly, various lattices occur. And he found, I mean, my understanding, he never worked before that in vortex algebras, but he found actually, you know, mind-blowing, so to say, a free field realization of the homology vortex algebra. So you take, you know, homology of the shape, homology of X, toric of this thing. That's a vortex algebra on general grounds. And he realized it as, you know, he took almost a certain lattice vortex algebra. Except that he needed to degenerate it. So what's a free field realization of something? Well, you take a free field algebra, something like this, and then oftentimes a kernel of the screening. In this case, it's more complicated. A differential. So he introduced a pair, a vertex algebra and a differential. And then homology is automatically a vertex algebra. He obtained this. It's quite amusing, remarkable, as I said. And he put it to good and non-trivial use. I guess that's all I can tell you. To me, you ask me applications. Have I fulfilled my duty? That's all I know, more or less. Any questions? All right. Now, so far I've been, and this whole project was like doing physics. So we've computed lots of attractive to some eyes stuff. But the question remains, what is it that we are computing? So yeah, to borrow from Feynman. So we would like to give a definition to the various objects that we computed. Just as we did in the style of what we have done at the beginning. I gave you the definition of the algebra of differential operators, and then we computed it and used it. And we reconstructed it in the universal enveloping algebra style, L.4, etc. So we would like to do something like this in this situation. All right, this is as follows. So let's try to understand this. So let me return to this more general situation of a smooth ring, except that now I will even require more of it. This is even less standard situation. So good, meaning that not only A is free, but it has an abelian basis. Then, if you give this a little thought, you will realize very quickly that what I did for C can be done in this situation. So we do have D chiral over A in this situation. defined as before. So it's essentially, if we denote the basis somehow, let me use taus. I will perhaps have to use the vertex algebra derivation though, which notation may clash with dxi violently. So let me at least at the beginning write tau for those coordinate vectors. So that's what I'm talking about. A thing that goes in layers and has A on top, then omega A generated over A by, well, if you have vector fields, then locally you can think that you have both vector fields and functions. So dual bases of the cotangent bundle. So I will have to write x1, x2. You will now realize why I insisted on doing dimension 1, because there is a painful clash of indices. You see what I mean? And likewise, TA, but now it's spanned by those also with an added index. And so it will go. The next level, I will have another copy of omega spanned by xi minus then omega A squared, where you have xi minus 1 times xj minus 1. And likewise, the vector fields. The vertex algebra structure is defined exactly by the formulas I introduced last time. The relevance of this condition is also obvious, because this is what, that's how the beta gamma system is defined. So the reason it works is not trivial. It looks very simple, but it's non-trivial. Beta gamma system somehow works. If you change things a little bit, they must fall apart. The notion of a vertex algebra is capricious. If you start with non-commuting vector fields, you can run in trouble. And there is even a theorem that describes precisely how you can run in trouble. Is it clear? So we will use this as a test example. You see, we want to give a definition of what we have in front of us. So we would like to realize what's the fundamental properties of this object. The first observation I would like to make is that it is filtered. Let me see if I'm not forgetting anything. Apparently not. How is it filtered? Well, this has to be contrasted with the discussed case of the differential operators. The differential operators are filtered by the degree of an operator. That the number of, in the smooth situation, this is what we're doing, by the number of vector fields occurring there. So a filtration is defined, informally speaking, by assigning to tau with no matter what index the degree 1. And so you will have d chiral A 0. That just can you guess what it is? Probably I should. I wanted to say that's an A. Is that true? Look at that picture. The 0th component is what you see leaning against this wall. So it's not only A, it's one forms, so to say, many copies. And then product of such, so it's everything that doesn't contain any taus. So this is not an A. This is what later will be identified canonically with the corresponding jet algebra. We will talk more about it later. And then there will be, so on the face of it, this is the rest will be modules. This is, of course, looks like a commutative associative algebra. So this is a module over this with an infinite basis. I arrange through a finite set and then infinitely many possibilities. And so it goes. Of course, this, as I said, is to be contrasted with the case of differential operators, where the filtration was defined like this. How did we use this filtration there? Mainly to consider the corresponding graded space. Does it make sense to do this here? So, observation. How is this filtration interacts with the vertex algebra structure? It actually is a filtration of a vertex, namely the end product of different components lives in the component So I haven't talked much about how you reconstruct the products from those fields that generate the algebra, but I guess I'll have to leave it out. If I start explaining this, I will never finish what they want me to make you to say something about. Well, maybe I'm addressing you not this thing because I know from experience students never cooperate. So if somebody really wants me to explain, I will. All right. That's a trivial observation. There is a subtler observation that will really help. So, of course, that's component number I plus j. It contains the previous one. And the important point on which everything hinges is that this embedding, this subset actually lies here if n is non-negative. This is easy to explain. This all starts, remember, we definitely had this. So all positive operations are generated by the fact that the zero product of the vector field and the function, in general, we discussed this in some detail. This is the derivative of f along that vector. Now, consequences of it, the whole point about positive product is that at least one vector field disappears. In complete analogy with what happens there. There the mechanism is slightly different, but very similar. There you just multiply. And at first glance, nothing happens. The number of vector fields is the same. But if you want to write it in a more economical form, you want to move all vector fields to the right. And along the way, some of the vector fields may hit an x and disappear. And that's the reason why the corresponding graded ring is commutative. Exactly the same thing happens here, as I will now elaborate. So, corollary of the discussion, which I will carefully draw. the associated graded, it's a vertex algebra because of this simple condition. That is, in fact, because of the second one, the commutative vertex algebra. In fact, a vertex now I will prove it, and then I will arrange things so that by the end we will have the definition of the vertex Poisson algebra written on the board so as to answer a question from yesterday that was not answered completely. All right. So, what is it that follows from? Yeah, give me a second. So the graded, of course, is the direct sum of the options. You define the operations by, choosing outputs. Yeah. So you define the products. As usual, by choosing representatives. The filtration condition ensures that you get a well-defined map like this. X in the force automatically holds. So this is all a consequence of more trivial observation. But less trivial observation about the non-negative operations implies that we get a vertex algebra such that, I apologize, but I will always be writing n, no matter in what algebra will work. So this newly defined nth product is 0 if n is non-negative. Right, because it's elapsed. If n is positive, then the image actually is here. And if algebras with non-negative products equal to 0 are called commutative.
So I have a question. So if we apply the Arakawa's abstract construction, it has the VOA and you have the Poisson VOA. To this case, do you get the same thing?
His construction works the other way around. Well, I will come to that, but his construction is quite different from that. He says that Poisson gives you a vertex Poisson on the jets. What we are doing is going.
Yeah, but he has another theorem. You have abstract vertex there. Then you do filtration in sort of things. Then you.
It's Lee's theorem.
It's a Lee's theorem in a different situation, in a quite different filtration. But
okay.
of course,
it's not the same.
No, it's essentially the same.
So if you apply.
It's a decreasing, that is increasing.
It's
yeah, well, of course, but there is no claim at originality here. Yeah, it's a standard construction. I'm not sure I understand your question. It's a standard. It's in the book of Frankel and Benzvia and in any other book. So if you have, if it's like the usual associative algebra, if you have an algebra,
I understand this. For the
okay, what's the question?
So D or Arakawa, they have a construction of it. Starting from abstract being you have.
It's just as I said, you have an abstract VOA with filtration.
So you don't assume anything. Just assume the accent. You don't assume anything because the Poisson VOA is the same as the same.
Yeah.
Oh, that's Lee. That's exactly the. That's Lee. Please. You told me. This is much simpler than this general construction. But yes, I guess it's not obvious. It's not quite obvious. But can be derived from that. So once you have this, and this in a sense explains the name. Remember, a vertex algebra, whatever it is in particular the collection of a vector space and the number of operations. But if it's commutative, then the pair, in our case, GR, operation number -1, and the derivation, that's also part of the data. Is a commutative associative algebra with derivation. The reason for this is the Borchev's identity, which I will have a chance to use more today, and therefore I will reproduce it. I cheated last time by not giving you the definition of a vertex algebra, but at least I should have said that this is a collection of such data plus the Borchev's axiom. And that the most important part of the Borchev's axiom is the following bracket. It's so important that I remember it by heart. It's not very simple, but memorable. Oh. I could have written to infinity, but the binomial coefficient takes care of values of g greater than n. The point of this formula is that operators of such multiplications commute provided the positive, see by vanishing of the positive operations has anything to do with commutativity because of this formula. What is commutative? The family of operators of multiplication. If it's with 0, then we get a 0. In particular, -1 commutes all products, all products by all elements, number -1 commute with each other. So that's a commutative algebra. D is the derivation of all products, not only of this. So we've got a commutative associative algebra. But the 0 multiplication can now be put to good use, just as we could use in the usual associative algebra situation the formula for the bracket, even though it vanishes, but if it vanishes in this regular manner, it can be used to define something on the something non-zero on the graded object. So now redefine the non-negative and products on these components. So ordinarily, the silly nth product goes to I plus j, but we know that if n is positive, it necessarily drops down to I plus j minus 1. So let's quotient out to get an element in this quotient. It's a standard exercise again for students to
-2.
yeah. So exercise, think of it. So it makes sense, but probably I should have formulated the exercise in a second because now there will be statements. So the outcome is as follows. A vector space V happens in this case to be the graded object, which is a what? -1D makes it an associative commutative algebra with derivation. Associative commutative. By the way, why associative? I explained commutativity. I haven't explained associativity. It's not obvious. Follows from the Borchev's identity. exercise for the students. So just as I said, think about all these constructions. Very good exercise in the beginnings of this theory. So associative community value. Next, now we have many more operations. Yeah, there is a unit element. So it's unital because there is this vacuum vector. So it's unital. Next, we have another group of data, same vector space, but now a bunch of operations, again with derivation. What do these satisfy? Well, first of all, the Borchers identity. It's there. We define stuff by picking representatives. So new identities may arise, but the old ones cannot be destroyed. So prove it. So Borchers, not the entire identity, commutation. And then there is this funny thing, which in this theory typically called skew commutativity. So if you compute skew commutativity, in the usual definition of vertex algebra, it's a non-trivial consequence of the axioms, but true nevertheless. So if you multiply like this, you may want to compare the result with this. Sometimes they are equal, sometimes they aren't. So there is some relation. That's called skew commutativity. So there is an overall sign. If you want to write it like this, you don't get the correct result, and there are corrections. Another formula so important that people tend to memorize. So the rule is, let me write the next term, will be dn plus 2a. You will have to do d twice, and then you divide by 2, which in fact is 2 factorial, and the sign is Nash. The sum is virtually infinite, but in reality, thanks to one of the axioms, for each a and b, it's finite. So, have I proved something? No, because I haven't given you the definition, but the definition is in front of you. So, there's a bunch of data like this satisfying these two is called vertex-Lie algebra. I will soon have I hope, I will have a chance to use the Davidson-Brinfeld language. They call it Lie-star algebra. So vertex-Lie algebra. I don't have to comment on the associativity and commutativity. So I forgot to mention the last topic. So there are first, second, and then there is the last one. That's the compatibility condition. So each operator like this is a derivation of the favorite product. So meaning a and b minus 1 c equals exactly what the Leibniz dictates.
Sorry, I'm a bit lost. May I try to? So what you said is that if we have, because of this grading situation, we pass the graded object, and then for the negative operations we take literally the ones that are inherited from the grading. For the positive ones, we take the one that are inherited by this additional stack.
Also inherited.
Yes.
Just
yes.
a bit more careful.
But with a more careful consideration of the and then you're saying with these structures, the graded object is an ordinary vertex algebra. It satisfies all axioms, plus some additional ones. And these additional ones turn them in a,
Yes.
that's the statement.
Make them a vertex plus.
Which one is the additional ones? I mean, they look like, for me, they look like
So those n is not negative.
They are, yeah. So this is different from the vertex algebra axioms in many ways. First of all, we are not considering negative operations.
so it's not a vertex algebra.
It is, but with respect to different operations.
Yes, but I mean, what I'm saying is you define the negative ones and you do positive ones in two different ways.
Yes.
But then you take them together,
Yes.
and then they are vertex algebra again.
No. So it isn't. It's a vertex plus or no.
So it's not a vertex algebra.
It is a vertex.
It's a commutative vertex algebra, and the commutative vertex algebra is the same as the differential algebra.
Yes.
So the first line defines.
Right. But and then, so what is the role of the positive operations that you get from this additional grading? They do not form part of the ordinary vertex algebra.
No.
It's kind of different algebraic structure.
It's different algebraic
Vertex free
structure.
algebra structure.
And this is very confusingly called a vertex Poisson algebra.
It's not confusing. It's very, very, it's very well called. No, it's not confusing. Yeah,
No,
it's a very nice. Now, many names on this theory
Yes,
that are unbearable.
No,
But this is a very, very nice.
Sure. It's me who's confused. Yes, that's true. I'm
All right, so the exercise was, of course, to verify all of this. All right. Remember, what is it that we're doing? We wanted to understand the meaning of the object, which D curl A was constructed by R. And we would like to understand its meaning. What is it that we constructed? The suggested way to do so was, let's first simplify. So having started with, we have obtained this. That is a simpler object. What I want to say is that we can understand what's that. So this is a vertex Poisson algebra. In fact, as the Chiral told us yesterday and has been said out loud several times, we have a different object that's canonically vertex Poisson. So what we have to do is take a Poisson algebra, in this case manifested itself as the free commutative algebra on vector fields. It's the commutative associative object. Then take the corresponding jet algebra. And that's canonical vertex Poisson. Such was the lemma that Arakawa's lemma that Fedor mentioned last time. A little more geometrically, you can put it like this. This is the ring of functions or the jet scheme of the canonical Poisson manifold. Complex manifold X, where X is max X. What I want to say is, if you understand this construction, then you will have no trouble seeing that this thing is absolutely naturally isomorphic to the one we've just obtained in the following way. R vertex Poisson algebra. I don't want now to prove Arakawa's lemma.
in order to compare the two results. But Chiral last time hinted at how it can be proved, and so I leave it for you as an exercise. So you want me to write it. So if we have a different algebra, I don't know, B Poisson, then you take this algebra, and I will remind you, just in case, what I mean by writing like this. So the vertex Poisson structure there is defined as follows, and by induction. So it canonically contains B, and the Poisson structure is uniquely determined by the requirement that B1, B2. So the n product of B1, B2 equals the Poisson bracket for B we started with. So equals this if n equals 0 and equals 0 if n is greater than 0. And then can be extended to the whole thing you need. So verify. At least doing starting at the beginning, you will immediately see stuff that we have already seen, and that will be very convincing, I promise. All right, so we've got at least some canonical objects. You won't argue against this being canonical. Therefore, so is this. In fact, we can now slightly geometrize all of this. Remember, in the end of the day, we would like to obtain shifts, so we want to do stuff. That's the game we've been playing. So we can now do the following. If we have X, the cotangent bundle, then we can extend this to the jets. We can consider, call this composite map phi. So living here, of course, is the structure. It's quite clear that it's a shift of vertex Poisson algebra, because that discussion of there is natural. This Arakawa's lemma is natural, and Chiral mentioned it last time. So this is a shift of vertex Poisson algebras, and so living here is the most straightforward direct image. Of course, you will now observe that local, so for a good U where there is a basis of a building basis of vector fields. So this shift over the space of sections over U is isomorphic to the curl of the corresponding algebra stuff functions on V. Right? I just repeat myself. It's something tautological. what this says is that this thing is a quantization of this, hence locally quantization of that. So now finally we can make the following definition. Is a vertex algebra or ship of vertex algebras, of course, such that it is a quantization of this canonical, such that it carries a filtration. There is even a chance you'd better, is it true, to use the filtration as part of the data. I'm not sure. Probably not. Just carry the filtration such that the corresponding graded object is isomorphic. So that canonical power has shapes of vertex plus on H. So, the problem is very simple after all. Remember I told you, we have finally classified all quantizations of the cotangent bundle. So that's what algebras of Chiral differential are. Quantizations in this particular sense. There is no canonical notion of quantization. Filtration quantizations of the jet cotangent. All right, it's a great success. I think. I'm sure you will agree. We'll continue after the break. Sure.
Now that I have learned that there's not only vertex algebras but also vertex Lie algebras and vertex Poisson algebras, the question is close to saying that if I start with an operator, say defining a type of algebras, is there a method to define the vertex, the corresponding vertex stuff too?
This is a murky area. So there is a rather complicated definition due to Wang by means of what he calls quasi-operator or something like this, which I don't really understand. There is, I think, really something that all mathematicians should learn, but probably doing so and very slowly. The language introduced by balance and principle. And this is something I will, time permitting, say some words about. So not so much opera, but Lie algebras and stuff in appropriate pseudo-tensor categories. So they replace the notion of an opera with the notion of a pseudo-tensor category, and then all this is straightened out. Yeah, so there is a way to do that. Any other questions?
So you have a 15-minute break.
Mm-hmm.
So one thing, this is a shape of potential part. We push forward. This is a justification of this guy's.
So now start the second half.
was waiting for you.
Oh, sorry.
I was thinking about your remark that the definition is not natural. Look, let's compare it with the usual construction. Associative, not necessarily commutative algebra, field that go to the graded object. You get a similar type of object, but simpler, automatically commutative. But sometimes, if so, it may carry an extra non-trivial structure that keeps traces of non-commutativity before, called Poisson bracket. It's exactly what happens here. In general vertex algebra, you go over to the graded, you get a vertex algebra, but it carries an extra structure of these new positive operations.
I think I got the point.
All right, how do we classify such? Now you will see why I spent so much time on reviewing this Bernstein-Valence on discussion of listed differential. So there it was similar. It's a quantization of the algebra of functions on the cotangent bundle. So it's generated by vector fields, except that there you not always can distinguish, you can not always can extract vector fields from functions. So the whole discussion started with an exact sequence like this. And what was the structure in? So that's a commutative associative object. That was a Lie. So all of this is about an interplay of an A module structure and the Lie algebra structure. So this is a Lie algebra, meaning that it's an A module, a Lie algebra, and the bracket is not a commutative, but is the measure of, excuse me, not a linear, but the measure of nonlinearity is via the action of derivations on functions. Likewise here, an A module and the Lie algebra, and nonlinearity is measured via by means of the anchor. What do we have here? If we have, yeah, I should have said. No, probably I shouldn't. No, that's all right. So, what do we have here? Let's return to the example. And it's quite clear that in general, all these. So let's see what abstract properties can be assigned to the example we start. It contains this, and the quotient is this. So what's that, by the way? Well, we kind of agree to understand what this. So if out of symmetric power you leave just one, these are elements from here that are linear in vector field. That's all. All right. So the graded object is clearly generated by this and this. And so it's easy to understand that the actual object is generated by that. Strongly generated, this is called in the theory of vertex algebra. So it's really, what we really want is to classify such sequences. But what does it mean such? So what structure is encoded here that we really want to keep? Let's list the structure, and then the definition will be, we will accept all of this by definition. All right, so that's easy. It's a commutative vertex. Well, it's a ring with derivation. So a commutative vertex algebra. What's this? Well, permit me. I should say that I don't have much time, so my exposition will be slightly, probably not so slightly, like-minded. So this is going to be a let me put it this way. We start by analogy. We start J infinity A algebra. What do I mean by that? So, first of all, J infinity A. Well, this is a commutative associative algebra with derivation. So, on the node, J infinity A module. We start, and then I have started to quietly slide to Taylor's and principal language. Because by the way, all this exposition, our work on that was done differently. In a more naive, more perhaps computationally explicit, but more naive and much less, how to say, conceptually clear way. So this is a quite remarkably illuminating approach of Galenson and Principal. So I'm talking about small bits and pieces that I could pick up from their book. Perhaps you already see by the terminology I'm using. Anyway, this is this star, that's their name for what. So they're talking about things much more general. Time permitting, I'll say a few words in what way. A particular case that's referred to by the word vortex will recover from, will identify this star with the vortex. And the two structures must be compatible. So this is all about nonlinearity being measured. You see, you will notice that there is, as they would say, there is a least star action of this direction of this vertex algebra on this algebra. You may wonder what I mean. Well, first of all, you know, it's just the adjoint action. You see, we discussed that. So just, as I said, I have very little time, so not everything will be defined. I'm just trying to show you that in what I'm about to explain, I may be using new terminology, but almost everything has already been defined. So this whole thing is a vertex Poisson algebra, so it acts on itself as a adjoint action, as that of a Lie algebra, of a vertex Lie algebra. This is a subalgebra. You can easily write formulas inside our example and see exactly what the commutation formulas are, and in particular you will see that it acts on the functions, so to say, nth operations with elements from here and here give you elements from there. That's the action I'm talking about. And this action is the measure of the bracket being nonlinear, just as in the usual case. So the the action, I mean the commutative associative algebra action. Is a Lie star module So this vertex Lie algebra acts here and it acts there, and naturally, and this is a map of modules. This is the way to formulate this. What I'm generalizing there is quite clear. So the map I'm talking about here is like this A tensor TA to TA. This and this are Lie algebra modules. And the formula that this equals phi of A psi plus A bracket of T psi says precisely that this is a map of K modulus. Okay? The same thing happens there. All right. Now this object. It carries lots of, just as that one, real algebraically A algebraic. So this is also a, there are several difficulties, I'll talk about them. But this is a vertex-free algebra, permit me to call it V-star algebra. So that so here is the first circle. I'll write it like this. That's a chiral G infinity A module. So what is it that I'm talking about? This is an analog of the phrase here, that was a G sub infinity A module. Here is the subtlety, and in fact, it's a similar but fundamental thing. It was actually observed by Borchert in his remarkable first paper on this subject, like page long, but the content equals dozens of volumes. A commutative vertex algebra is the same as a commutative associative with derivation. But the notion of a module over commutative associative vertex algebra and a module over it as the usual commutative associative algebra is different. And this is what I'm emphasizing. So G infinity A acts on that thing as a simple, commutative associative algebra with derivation. It also acts here by the very definition. That came from a vertex algebra. That's a vertex algebra. So of course it acts on the whole thing. But this action is not one of a commutative associative algebra. It's an action of a vertex algebra. Let me explain this. Let me show you. That really is the point of all of this. The rest is, to the point, will be simply listing some of this property. So what, if you have a vertex algebra, what does it mean to have a module over this? Well, to have a vertex algebra means for any V to have an operator, a family of operators acting there. To have a module over a vertex algebra means to any V have a similar family of operators acting there. And these must satisfy an identity that can be read off as a Borchert's identity. Here is an example relevant to the situation. So, axioms. So, for example, suppose you write A minus 1B M minus 1. So it is applied to an element of M. So the requirement is that, of course, it's like, we like thinking of this as A times B. So we want to have, of course, that A times B applied to M equals this. But that's not true. What Borchert says is that the definition, I'm about to unravel for you the definition of the normally ordered product. So there are correction terms, I guess, like this. Now, B should go there, and zero M, etc. So a bunch of terms like this with this index increasing, or the other way around. So that's what you have in the module of, that's an example. Now suppose V commutative. I haven't assumed it. Suppose V commutative. If V commutative, it means that, for example, it basically means that they all these guys commute. V, I don't know, W. That doesn't imply that the corresponding operators on the module equal 0. So that's the difference. So you get, so that's M, a vortex algebra module, even if it is it is a, so this is a chiral, V is a, M is a chiral V module. It's when such identities coming from Borchers code. Now M is a just V module, that's the terminology I try to use, is when this looks like what we wanted it to. So this is equivalent to demanding that A and M equals 0 for n non-negative. And it doesn't have to be so. And it is not in the example we're considering. In our case, suppose it's even when A is, one dimension, or rather, the manifold is one dimension. So we have C of x naught, x minus 1, etc. How does, for example, these subindices are different, their meaning is different from their shift. So how does x naught squared operates on d minus 1? There will, of course, be a term like this. But there will also be my personal struggles with this problem those 75 years ago started with carefully figuring out this. You never get it right, however hard you try. Something like this. I won't put more than a penny on me being right, but something like this. There is a correction term. No. Just x minus. Young chap. Is it right or not?
I don't remember.
It's next to impossible to get it right. It's quite miraculous that this project worked, because you have to verify formulas like that. There isn't. However many times you compute, you never get the same answer. Each next time you compute, the answer is different. Anyway, that's the phenomenon. That's so important that, so, I don't know, probably it's not very important, but Davidson and Greenfield introduce at this point the terminology. So they say that M is a central chiral V module. If, well, in my language, in this naive language, they would put it differently, but you know what I can, people like things, formula-less statements. It's called central chiral V module. Let me make a digression. Here is a nice way. To formulate. there is a functor from vertex algebras to Lie star algebras. Forgetful functor that sends V, which is a bunch, V and a bunch of products. You just forget about half of them. Right? It means that there is a functor from V modules to V star V modules. V modules when V is regarded as a Lie star algebra. So
This
M
is
goes,
same as the, sorry.
M goes to Lie of M. So a module is called central if the corresponding Lie star M is trivial. Nice, isn't it? I have thoroughly obscured the matter, perhaps, but it sounds good. Do you agree? Just a fancy way to.
So is Lie star the same thing as the class called the component algebra?
Yeah.
Same thing.
Yeah. All right. So to return here, so you see, so we will have a chance to use this. Terminology. All right, let me keep on discussing the structures. So of course, I will say it later on, but the arrows are expected to preserve all the structure. In particular, it means that J infinity A inside P parallel 1 is a Lie star ideal. Being a Lie star algebra, probably, right here. So this thing acts on itself as a Lie star algebra. That's an ideal. So it acts here. How does it act? Well, in principle, it could be anything, but here is a requirement that was also imposed if you live some pages back in the situation of the usual differential operators. The restriction of the joint action to J sub infinity A is just a pullback. So this thing acts there. And mapping first here and then acting will give you an action. This is it. Is here the pullback. Pullback. Let me sigma a yield. So pullback with respect to sigma. And this is almost it. So just as I said, the arrows preserve. This is a requirement, it's not a theorem, it's a fact. Preserve all the structure. I leave it for you to think about it. So I already mentioned that sigma must be Lie star morphism. Now look, for example, J infinity A acts on itself, but it also acts on the image, and it is embedded there. So another action then arises, and they coincide. So there are a lot of things like that. I will only mention the following non-trivial property, which actually is responsible for the interesting things happening. Look at sigma. J infinity A acts on both. And so the arrows preserving the structure, apparently, I want to say that this is a morphism of J sub infinity A module. But it doesn't really, doesn't make sense to say it just like that because of our discussion. These are modules of a different type. So what I want to, what actually happens, and I would like to emphasize this, is as follows. So, in particular, look, J sub infinity A acts, well, it acts on D and it's on itself, so it acts on the quotient. The latter module is central. It follows from the definitions. And therefore is just a module over Chiral A sub over J sub infinity. So the requirement is that sigma is a morphism than of such module. So with all these preparations, definition simply axiomatizes the situation. So you just mentally replace forget about the requirements on A and mentally replace the familiar object in the middle by something. So that's the definition of a chiral J infinity A algebraic. An exact sequence such that, and everything we discussed, so L chiral infinity carries all that structure to objects at the ends are canonical. So all these properties must I should say at this point in what way this is different from what we did at the corresponding point of the discussion. I mean the paper of second. we dealt with an object that's much smaller and computationally perhaps easier to handle. So recall to this, first of all, in vertex algebras, we're so used to dealing with conformally graded objects. So this is not a requirement. But for us, at least psychologically, and of course for computation, it's very helpful. So we focused on the component of conformal weight 1. It was quite clear that locally you have a direct sum, but if you try gluing, that's the whole point. You really have the exact segment, and elements of TA may generate elements there, so the segment is not naturally split. So this is what we call a vertex algebroid. It's much smaller than this, so this thing really, that's like that. So K infinity K, of course, has this. That's the derivation that's there. Here it coincides with the usual Durand differential. And so it goes on. This is much bigger. But of course, in the graded situation, all the stuff is hidden in this second floor of our diagram, and it's very small. So it's nicer, much nicer to compute with. But conceptually, it's God knows what. Frankly, I myself don't quite understand the definition of a vertex algebroid given there. Because of what? The idea was, so the whole thing carries all those operations, a complicated object. But there's this huge Borcher's identity. It's huge and very unpleasant to look at, but at least it's one identity. What we had to do here is to consider a bunch of partially defined operations and see what part of what parts of Borcher's identities can be restricted to this space and what do they give us. And so the result was a collection of 2-3 partially defined operations and disparate pieces of Borcher's identity. So it's quite, once you've got used to all of this, you compute without problem. But conceptually, that is, of course, nightmarish. So the fundamental issue, for example, is, of course, in this whole chapter of mathematics, the derivative is important. But this floor is not closed on D. There is part, tiny part of D survives. It's an operator from A to omega, but T gets out of it. So there are many things like that. And this is conceptually absolutely clear. So how can one use to classify that? Now, I have very little time, and I'm sure that I won't be able to really to define anything. It's really what, in the remaining time, what I will try to do will be a pitch, a bit of advertisement for the payload from Brinkel theory, because I will show you that if you understand the definition, then the classification. So remember, classification. So recall that in the case of usual differential operators, the result really was encoded by this truncated Durand complex. So objects are labeled by elements from here and morphisms by elements there. a quick way to say this, I'll just remind you of the word, is to introduce this simple category with these objects and these morphisms essentially. So the result is that the category of such is equivalent to this category. In fact, this category acts on the category of whatever that means, on the category of such extensions, and these extensions, which are the algebroids we call them, is a omega 1 source. So it's like R is the same as any straight line on the plane, it's the same as R. More precisely, any line on the plane is an R or star. So this is exactly the type of statement we've obtained. So what I want to explain, and I really won't have time to tell you much of substance, but the point is, if you know the definitions, you will soon even lose, you won't see the difference between this case and the vertex algebra. So there is an analog of this. So there is a BD call it Chevalier Durand complex, defined for any Listar algebroid. In our case, it's like this. So it's the whole thing, C naught, J infinity A. So that's like functions, and that's like vector fields. So in finite dimension, you can more generally talk about, you consider the algebra of vector fields with values in functions. And if you insist, you can consider linear over functions, such, Cauchy. So it's just a Lie algebra. You have Chevalier cohomology complex. Something much simpler than was mentioned today when discussing the Hamiltonian reduction. Hamiltonian reduction is a more complicated version of this. So any Lie algebra, any module, it's a standard Chevalier complex. If your algebra is an if your algebra is an algebroid, then you can consider chains that are linear with respect to the ring A. So you will get a subcomplex. So the point is that with all the definitions in place, like this automaton starts playing its tune and produces for you an analog. So this is like a Lie algebra, and so it will have its own complex. And in this situation, when there is an extra ring flying around, you can consider subcomplex of Cauchy's linear. This cannot be defined. And so it will go C0, C1. So the point being that you can introduce, what you have to do is to focus on the corresponding truncation as above with the same degrees. Yeah, there is a differential. It's defined in the same way, so you can take both. And you define the corresponding category. Objects are these, and morphisms are measured by those things. And so the obvious result, as obvious as the discussion of the ordinary situation, is that the category of our category of Chiral algebroids is this thing. achievement of their theory. It really is. It takes some time to understand definition, but once you've got it, it becomes quite clear. I'll try to, I'm so grateful for you to patiently listen to me all this time. So I'll try to entertain you. I'll try to tell you something I'm using in the remaining time. But since I've got there, I haven't really explained anything. It's just an advertisement. But permit me to first finish. So it's a huge complex, and I really don't know what the actual answer, for example, for so equivalence classes would be exactly the Chevalier-de-Ram homology. This modulo the exact cochain, and I don't know what the answer would be. It could contain the answer we've got. It would also contain something else. Certain small pieces of it can also be identified. This I will now quickly explain. So let me very quickly explain the formulation of all of it. It at least is easy to state. So that's just a tiny part of it. So our result is singled out by the condition of conformal grading. Conformal grading. So return to this push. So the whole thing is generated by function. Functions by themselves don't carry anything interesting. So the whole thing, at least as a vector space, is a sum of that piece and of that. Conformally graded means that so P is a direct sum of pieces, and Vn J Vn belongs to Q is if somebody remembers, n plus n minus j minus 1 or something like this. Yeah, I think if n is minus 1, then this minus 1 goes away and this goes away. Something like this. So if you look up this definition, what you will realize is, so the whole point is, if you look at those axioms or anything, you will realize that the only thing that we don't, remember, it's exactly the discussion we had a couple of days ago. So we give ourselves two alleged vector fields, and we are thinking, what can we do about the nth operations? And a little thought will show you that the only thing that is not quite determined is the zeroth operation, and operation number 1. That space is closed only under these, and the other operations were then greater than that. They are equal to 0 if n is greater than 1 because of this condition. And because everything starts at degree 1, then there is degree 0, and then there is nothing. So this is the only thing that potentially we can have some control over. This can be here, there is no room for maneuvers. It also is very easy to understand in the smooth situation. So it's this feature that can be varied. So the product, the zeroth bracket of two vector fields is an element here. The axiom implies, if you look, I carefully explained all of this, and you will see follows from the axiom very easily that modulo omega A, the result is predetermined. is the product. The rule of thumb is operation -1 is like the usual multiplication, and operation 0 is something like the usual product. Something like in this concrete situation means precisely what I said, that modulo 1 forms is the usual product. The axioms fix that. So that's what remains. Yeah, by the way, so however we define it is as follows. You just take this, really, I mean, it's boards to write down, but it really is just listing down the properties that are in one-to-one correspondence with the ordinary situation. So that definition implies what I'm saying, and is equivalent to this with the homogeneity assumption. So what can be said about this thing? Well, read the paper. This is some things that are easy to verify. So what's that? Alpha is a map from TA cross TA to omega A. You can play a little with it, and you will realize that it is a linear. There are various properties that follow from the Borcher's identity, and you will see that it is anti-symmetric in some total manner. So in the end of the day, it's anti-symmetric with respect to this. So you can think of it as a map like this. Lambda squared A to omega A. You can dualize and you will get a map lambda squared A tensor A. It's totally anti-symmetric. This is all easy consequences of the Borcher's identity. So in fact, alpha is a straight form. That's easy consequences of the Borcher's identity. Here is another consequence that's perhaps not that easy, but much more amusing. One of the Borcher's identities is that, you know, if you have a vertex algebra and a zeroth operation, this, I told you, zeroth operation is a, we think of it as some kind of generalization of the Lie bracket. This pair is not a Lie algebra. Anti-commutativity is violated. It's replaced with this complicated commutativity. But a certain form of the Jacobi holds on the node. What is true is psi naught A to naught tau minus A to naught I. I'm trying to say psi, but avoiding putting brackets. What this, and that's true in any vertex algebra, what this implies in this particular case is that alpha in fact belongs to the space of the closed straight forms. This is all easy. What's not so easy in this approach is to understand why such discussion suffices. So, as I said, in the previous example, that classification is of this type is almost tautological, and that indeed is true, but that's a much more complicated complex. Here it's much less obvious, but true nevertheless. We are moving in one direction always. We imagine having a vertex algebra. We are getting some properties. Why these properties suffice? That's less obvious, but true nevertheless. All right. So we see that objects are labeled by closed free forms. It's a familiar situation. How about morphisms? It's a similar story, and I suggest that you simply look at an example of deep chiral A that I explained and verify it. And it's a simple computation. So what can we do as far as morphisms go? So what's a morphism of such things? Well, this we know. We discussed before in the ordinary situation. So you imagine having a similar such particles. And the morphism is a map such that at the end it induces the identities. What does it mean in plain English? It means that a morphism sends a vector necessarily to itself plus a force. So beta, that's the one. So it's a map, beta, is a map from vector fields to one force. So this is a situation similar to this, except that dimensions went down. A very similar discussion will show you that in fact remember we had to fix operation number 1. If you do that, you are forced. So as such, it's the same as the map from T8 plus T8 to 8. In fact, you are forced to take it inside the anti-symmetric section. So that's an element of omega T8. So what does this map mean? So you assume that you have one object, and that means that an alpha gives you another such object. So, and then a direct computation will show so beta defines a map if you fix some alpha. And the previous discussion essentially shows that any object, if you have something to start with, then any object is L of alpha. And beta automatically a morphism from L of alpha to, what do you think? As before. For example, you will have an automorphism of this object if beta is closed. Otherwise, that will be a morphism only if you change your F. There you are. So all this means is that the appropriate. So the conclusion is this is all about the following truncated Chiral. It's pleasing to contrast it, check it against what we had classic. The dimension went up by 1. More precisely, the category of vertex algebroid, I think I'm using this terminology like this. Vertex algebroid is what's governed by that. So it's chiral algebroid with the extra conformally integrated assumption. The vertex algebroid is a omega, not 1, 2, but rather 2, 3 defined in the symbol A. Source. Now we know that locally on good subspaces where there is an abelian basis of vector field, such thing exists. So on any manifold, we locally have this category. In fact, you clearly get a sheaf of such categories. We just say that over any open subset, the category is all those sheaves whose restriction to good open subset is of this type. What remains, so it's, they say, is a geoid bound by this complex. I don't even have to write anything because I'm repeating my discussion in the case of differential operators. except that sometimes I use the word vortex or chiral. So we've got a jaw bound by this complex. So how is this? By the way, compare this with this. That was, it's a highbrow balance and principle stuff. It's even more similar to that result. It's just an analog of this. In a rather, rigorous manner, made analog of that in the situation of the jet ski. How is this related to that? So the actual statement, if I'm not terribly mistaken, is that this is a simply subcouplet which extracts the classification of conformally graded objects. And my discussion here simply gives you an embedding one into another. I haven't yet defined it in any way, of course, I'm just trying to create a picture. So, to finish with this, the last word. So up to this point, in what way the vortex story is different from the usual one, except from technical differences. Definition is different, identities are more complicated, but conceptually there wasn't much difference. But at this point we see one. We so far, all our examples, actual examples, were constructed only locally. We still haven't, well, we've seen a couple of objects defined globally, but we have no idea whether such objects exist always. So there is a computation that computes, so once you have a job bound with these words, so we've got a job of CDO is bound by vortex algebroids, bound by this complex. So is there a global, at least one global such shape? It's again a matter of, abstract nonsense. Whenever you have a jaw bound by a complex like that, you get a characteristic class, an abstraction to existence of the global object. And I guess it's also helpful to look at the discussion. So up to a point, there's nothing to compute. It's very easy. It's like our discussion of differential operators made a couple of days ago. So we consider by complex. So we consider a cover, the cover of our smooth variety X, and a truncated the round. So we have two differentials, the shell and the round. So is there an object, a globally defined shell? Let's try to build it. So make this fine enough so that on each UI you can pick such an object. So over UI you pick your L.4. Do you get a global object? Not necessarily. On the intersection, you have both. Li restricted to the intersection and Lj restricted to the intersection. They don't have to be isomorphic. No reason to believe in that. By the way, this discussion shows that locally isomorphism classes are of course simply the Durham cohomology. Omega 3 closed, mod out d omega 2. In the analytic situation for a for small enough subset, of course that will be 0. But in algebraic, even locally, there may be non-isomorphic objects. But even if they are isomorphic, there may be an abstraction. So, but anyway, in general, we can always say that one equals another plus it's a torsor, so you perhaps need to add a closed free form to one of them to get another. What it means is, so we place omega 2 in 0, omega 3 closed in 1, that's 0, check. So what we've got is a bunch of Fij on the intersections. Is there a chance that they close? Not that they can be glued together. So what you have to do is as follows. You apply the check differential to get a 1, 2 close. You kind of come back. The result is that even if you get non-zero, this is something automatically isomorphic to the initial one. So there is automatically an isomorphism, and that's given by a bunch of 2 forms. So there will be a check 2 co-cycle with values now in 2 forms. To which you can then apply the check differential again, and the result is automatically 0. It's easy to observe. What it means is that this bunch gives you an element in Z2 of this bicomplex. So the characteristic class is the corresponding element in homology, because you can vary it. Of course, you can change these by changing the objects locally. So it means that you can try replacing locally but gamma i's, and then on the intersections, the result will change by the check differential of those, and then you can try to reglue using forms there, and so you will have that. So the result is trivial precisely when it's in the image of the total differential applied to the previous one. Think about it. So Z2 mouse, so the element of this co-cycle in H2 is the characteristic class. So it's true whenever I have a category bound by this complex. Now in our particular case, we just played this game. We picked collection of neighborhoods, picked coordinates. On each we considered the complex, the Chiral AI, and then used transformation functions to compute all of this. And the result was the first contracting class. Or rather, its projection, it naturally maps into this group, and so its image is the abstraction. So for example, the abstraction in the case of CP1 vanishes for the zero-dimensional region. It's the second homology, that's one dimension. For example, it's very well known that for projective varieties, it is non-zero. For flat varieties, it is 0. I should probably, it's an interesting representation theoretically, so I thought to entertain you with balance and Differential, but there is so little time left. I'd rather talk a little bit about Chiral Differential operators on the group than this thing. You've written it, that makes more sense. So the main thing about balance and Differential is if you understand their definitions, then you can recast the whole story in such a way that you won't see any difference between Chiral Differential operators and the usual one. It's a quite striking result. But back to these examples. So So example number 0, this is something we discussed. So if you start with an abelian basis, of, so I'm thinking in terms of T. If you start with an abelian basis of the tangent of the algebra, then you immediately get the chiral A, simply stipulating that Ti0 Tj is, in fact, that's what you stipulate. Ti and Tj equals 0 if n is greater than or equal to 2. It's another way to reformulate what I did previously. There is a remarkable example which is an epsilon more complicated than this. It's also a fact. Suppose G is a simple equal. It's also in a finite. Think SLF. Forget therefore about shape. You have functions on the group. And you have a basis of CG. What do you think the tangent algebra is in the case when manifold is a group? You don't have that, but you have something more interesting. It's a free module over the layout. The Lie algebra is not commuted. This space is not commuted. So, yeah, and G is embedded there. That's your choice. Say, write invariant vector. T, G. So G invariant vector. You decide right or left. So in fact, you embedded through one of those. It's very easy to see. I could prove it. Of course, I don't have time. Probably it's quite a reasonable suggestion that you, if you want to study what I tried to explain, that you try by analogy, by hands, to build the entire vertex algebra. The same logic you have upstairs, C of G, then one forms. I don't have to tell you that one forms are also like C of G, tensor, reduced to Lie algebra. Last similar thing, G itself. And so it will go. It's easy to convince oneself that these conditions are absolutely unambiguous. So the point of all of this is that even though they don't compute, so this is a free CG module. I should have said. In this particular case, though, so formally, this is defined by analogy with example 1. You define your vertex algebra to be generated by functions and elements of G. And so the only thing you need to specify is their brackets. Well, that of course is like this. It's the bracket in the Lie algebra. If n is n, 0 if n is greater than or equal to 0. Totally analogous to what we've done. Can be done completely independently by hand. But there is an extra possibility. I wonder who sees what it is. This definition, you see, forget about functions. That's the way to define a simpler. So if you forget about function and simply try to imagine a vertex algebra defined by this relation, then what you will obtain, of course, is the vertex algebra that has appeared in this room on more than one occasion at zero level. This, of course, suggests that you play the same game, except that you say that tau psi 0 is the bracket, and tau 1 psi this, if you care about conformal grading, must be a number. Or at least a function. Suppose it's a number, for simplicity. Then the axioms of the vertex algebra will require that this be invariant. So G star S squared G star G invariant. So you need to fix an invariant inner product. And you define the first product of them like this, and the rest 0. So if you forget about function, that's a familiar definition of BG. And instead of the number level, I'll write the choice of the invariant form. It's the same thing. Absolutely the same argument will show you, we're running out of time, but I hope I'll be able to tell you something of content. That doesn't complicate matters much. It's easy to see that this gives a family of algebras of the same size. So D Chiral G, but now they get labeled by the choice of the inner product. If G is simple, then there is a one, so it's a C family of vertices. The theory that I explained, it gives you an abstraction. In this particular case, it's easy to see that the abstraction is 0, just simply because the tangent bundle is trivial. Of course, constructing is 0, so there's no abstraction. There are shapes. We've got a family of them. How many isomorphism classes are there? So whenever you have a germ, that gives you a characteristic class. The so H2, that's where characteristic class lies. So a characteristic class is 0, but then it's also another bit of abstract nonsense. Isomorphism classes are then H1. And in this particular case, H1 is easy to compute, and indeed C. And so this nice construction that marries, in a sense, representation theory with geometry of Q, gives you, a universal family of such algebras. Another minute?
Yeah, please.
So, this is a very important algebra of vertex algebras. It has been used in a quite non-trivial manner by people like Hipp, Gage, Gory, Frankel. I will finish. That will be probably my last or penultimate sentence. I'll finish by sketching how you can prove, for example, that the characteristic class on G mod B is 0, and actually construct the algebra of differential operators there. So you see, this is all about, classically, this is differential operators. This is going from T star G to T star GB. Oh, that of course simply is the Hamiltonian reduction. for which there is a complex. So the algebra of functions here has constant and Sternberg following Hagen explained to us. What we are doing, well, this has a chat analog. And this is was a classical limit of what we are doing. Now, classically, what this suggests is you quantize that to get dg. To get a thing like that, you have to do the reduction with respect to b, and then there is a moment map, and you pick a pre-image of the zero character and things like that. So the algebraic version of this, algebraic geometric version of quantum version of this is known. You do the simplified version of Frenkel-Sokolov with the zero central charge, so to say. So it is quite straightforward to write semi-infinite and semi-infinite homology of loops in Borel with values in dg. There is a snag, though. It's a famous observation in all this theory. This is Hagen's discovery that the differential there is the, so to say, a vertex, the singularization of the usual Chiral differential. Let me write it like this. The problem with it is that its square doesn't have to be zero. And the central charge, is responsible for it. So for this to be zero, this must be chosen to be critical. It's already quite remarkable if you think about it. So this geometric construction knows about the criticality of a certain invariant form. And then it works, and it gives you a sheaf. It's very easy to understand that the result is a sheaf of algebras of Chiral differential operator. It's a vertex algebra automatically. That's the property of this concept. So what is it? So this already gives you the desired sheaf there, therefore constructing class at 0, for example. But the question arises, what can we say about this sheaf? Does it know anything about G hat, for example? Now it really is 10 seconds. This shift is quite remarkable in that while G has two different embeddings of the Lie algebra, we talked about it, there is a choice, left invariant, right invariant. The remarkable thing is that by construction it's built to contain V. The remarkable thing, and that's a non-trivial, quite non-trivial observation, due to a heap of Gates glory, but actually going many years back to Hagen, is that there is a commuting, so this chiral items, there is a commuting with this one, different embedding of this vertex algebra. And what's remarkable is that this is an embedding at the dual level. Dual means the sum is twice the critical. Or minus twice the critical, perhaps. And so, since this only works for critical, so one G is killed because of the differential, but another survives. Critical. So it should be so that one critical, what survives is also critical. From this you find the right description. And so this indeed is a sheaf of G hat modules. The one that we consider is of course a particular case. the case of a cell field. And that's true in general, as this shows. And indeed, the space of sections on the big cell, as you can easily guess, the restricted Wakimoto module. In a sense, this is one of the simpler constructions of the Wakimoto module. Constructing Wakimoto module in general is very non-trivial. And it's not very easy, but in a sense, it has its advantages. It may be, in a sense, it may be even perhaps easier than the original Fedor and Malikov construction. It also deals with complicated homological issues. Totally different, but it's the same